Fine.
You can even type them if you want. Thank you very much,
Correct.
Alejandro.
Yeah,
The next speaker is Pratik Chaudhari. He's a junior faculty at the University of Pennsylvania. Pratik has done really pioneering work on the landscape of energy functions, and he is going to talk about learning with few labeled data.
Can you all hear me? Can you see my screen?
Yes.
Perfect. Can you still see my screen?
Yes.
Okay, perfect. So thank you for the invitation. Very interesting workshop, great bunch of topics. Today, I'll talk to you about some of the work that we've been doing on understanding and synthesizing algorithms that can handle a few label data. This talk is divided into two parts. First is kind of a empirical part where I'll try to give you an appreciation of why we care about learning from few data. And the second part is an attempt at putting some theoretical foundation for why transfer learning algorithms work well. So let's jump right in. Most of us would agree today that we are good at classifying data sets or solving problems where I give you a large number of labeled data. Roughly speaking, if I give you 100 to 1000 or more than that even samples per class, you are going to be good at training state-of-the-art neural network to do well on these images. I'll speak about classification, but that is simply a way to narrow down the focus. But in general, these ideas apply for other problems also. What we are not good at solving today is the low shot regime where I may have, let's say, 1 to 10 samples per class. And this is very pertinent and important. So for instance, imagine that you are a farmer in California who is growing strawberries on his farm. And you would like me to build you a machine learning algorithm that classifies all the produce on your farm. Now, this is not very easy to do because I don't have the data from the particular strawberries that this particular farmer grows. What I do have access to is data from the internet, right? Large curated sources like ImageNet or things like Flickr or Google Image Search. These are not the exact same data that this particular farmer has. These belong to the stuff that occurs frequently in our physical world: cars, cats, dogs, planes, name it you will. What I would like to do is pre-train a representation on stuff that occurs frequently, and then somehow adapt it quickly to a new data set that I am being presented with. The objective is, or the motivation is, if you give me data about the strawberries, and if you don't give me too many samples about the strawberries, I'm not going to be able to perform well on it. So I would like to use a large curated data set that doesn't really have strawberries or may not have strawberries to transfer onto this new set. There's also a third regime, which hasn't become popular yet, but it will. This people would call extreme low shot regime. When does a neural network tell you that I do not know a specific datum? Today, when you train a neural network, your world is divided into 1000 categories if you're training an ImageNet, and really the network has no idea of whether an object belongs outside these 1000 categories. So this is what people would call anomaly detection, or what we would call extreme low shot regime. This talk will be about the low shot regime. Here is one idea that we found to work very well that kind of completely changed my perspective of what few shot learning should be or could be. And it goes as follows. So consider that I have a data set DS. This is my training data set. And at the end of the day, machine learning boils down to you learning a function f that, given a new datum x, uses your past data dx to predict the labels of this new datum x. Okay, there is nothing special going on, just notation. Now, in principle, no one is stopping you from searching over the space of all functions every single time I give you a test datum x. That is very expensive to do. It takes a lot of time. So in machine learning, we summarize the data set into some parameters. These parameters are, let's say, theta star. They're a function of your data set. These are the weights of your neural network if you're doing deep learning at the end of training. This summary is necessarily lossy. So it is a statistic of your data set. How well the network performs on datum X depends on how well you train the network in the first place. You're not going to be able to train a good network if I don't give you a large data set DS, which is exactly the problem that we are interested in solving here. The good thing about the statistic is it avoids having to search over the functions f at inference time. Here is one thing you can do. This idea goes under the banner of transductive inference, and what I've written here is a loss function for what I'll call transductive fine-tuning. And let me try to parse this. Instead of searching, instead of trying to learn a good statistic from the training set, which is hard to do because of limited data, we are going to search over the set of functions a little more explicitly at inference time. This is exactly the textbook definition of transductive inference. And here is how it would go. As usual, the first term is something that is the cross-entropy loss. The cross-entropy loss is computed over all your labeled samples, NS. These are the training data. But I give you some test samples for which, of course, I don't know the label. So these are what I denote by NT. You're trying to improve the cross-entropy loss over all your training samples and test samples. And you have an explicit minimization over your parameters theta. In simple words, what I'm trying to do is take my trained neural network and fine tune it in a way that it works well on the test data. Now this is transductive because I'm not going to train, I don't really care about training a neural network that works for all possible test data that is drawn to the distribution of test data. But I do care about training a network that only works for these NT samples. And that is where you get the efficiency, both statistical and computational in transductive inference. The first term is the objective. The second term is simply making my job a little easier. It is a proximal term that keeps my parameters close to what I trained on the training set. That way I don't have to search over all possible parameters when I do the minimization. This is the fine tuning part. And yes, you may have a regularizer that is a function of your test data that is unlabeled. This allows you to pull in techniques from semi-supervised learning into transductive inference. So semi-supervised learning and transductive inference are close to each other, but not quite the same. You can borrow and give a lot of techniques across these two fields. In a nutshell, this is an objective that takes your neural network, adapts it to work well on new data, adapts it in a special way. And that tends to work really well. So I will not belabor this table. This is quite common in a lot of papers in this area. But these are few different data sets that are considered benchmarks in this world. And with transductive fine-tuning, or even with just fine-tuning, forget the transductive part, you are improving upon existing methods, not by 0.5 or 0.1%, but oftentimes by 7 to 8%. And that tells you that there is some merit to thinking about few-shot learning simply as a transfer learning problem. If I do well at transfer, I'm going to be good at handling situations with new data. You can run these kind of algorithms at scale. So this is the large ImageNet data set, about 21,800 classes, where you can split it very nicely into the frequently occurring classes in blue on the left-hand side, and then the rarer ones shown in green, which have up to, let's say, 10 to 1,000 images in this case, as your test classes on which I evaluate you. And this works fairly well. So well enough for you to be able to deploy this in practice. You get few shot accuracies of the order of 90%. With a few more tricks, you can bump it up to 95, I'm sure. And the moral of this story is that if you want to do good few shot learning, transfer learning, in particular transductive transfer learning, is a very good way of building algorithms. Can you always do this? Of course, if I give you test data that comes from very different classes, then it doesn't really make sense to pre-train your representation on your frequently occurring internet classes. And this is kind of how we try to formalize this theory. When can I do this? When can I not do this? What are general principles that always let me do good transfer learning? And I'll formalize it in the language of information theory, but this is simply a particular style. You can write down similar ideas using other notations, but here is mine. Most of us might have heard of Naftali Tishbi's work from late 90s, where I would like to think of my data X as being converted into a representation Z. What is a good representation? A representation that is good is something that can allow me to predict the targets Y, even if I throw away all the data. So Z is sufficient, and this is a statistical concept, to predict the target Y. I would like Z to also be small. So let's say it doesn't take a lot of memory to store it on my hard disk. It throws away a lot of information about my data X that is not relevant, the nuisance that we saw in a couple of talks ago. In general, a few bits are required to store Z. And Tishby gave a very elegant Lagrangian that you would like to minimize. It goes as follows. I would like to minimize my encoder Z given X. Encoders that are good throw away a lot of information about X. You can't throw away all information about X because then you won't be able to classify. So you also have a negative mutual information between Z and the target labels Y. Now, the key point of this Lagrangian is that in order to do well under the information bottleneck setting or for representation learning in general, you necessarily have to become invariant to nuisances. And this is something that everyone here would appreciate very easily. The moment you become invariant to nuisances of your current task, you don't know what to do for your test task. And this is exactly how we modify in the information bottleneck principle. IB says, throw away information from my data. Once I throw away information from my data, I have no idea how to recover that information back for my target task. So I cannot do good transfer learning. The IB principle is basically the opposite of transfer learning. Transfer learning tells you to build redundant representation. IB tells you to do very succinct representations. So we are going to play a little trick. We are going to consider a task, a second task that is simply reconstruction. And reconstruction is a beautiful task. It is kind of a, formally speaking, it is a superset of all tasks. If you're good at reconstruction, in principle, you should be able to use this lossless representation to perform any other task that I ask of you. So we are going to talk about an architecture that goes as follows. You have a standard classification network on the top. You have X going through an encoder, which I'll denote as E, into Z. Z goes into a classifier, which I'll denote by C, into Y. I secretly build a decoder to measure how well my model is doing on the task of reconstruction, and that I'll call decoder D. The objective is to simply use the decoder as kind of a measurement device on what Z is learning. You can now study a Lagrangian. This is a free energy. You can show that. This is simply the rate. The rate is the number of bits that are used to represent your Z that are additional as compared to what you would need for using some prior over Z. And the distortion is how well you're reconstructing your data given your representation Z. So this Lagrangian R plus lambda D is something that you've all seen, maybe not in this notation, but in different notation before under as elbow, the evidence lower bound. The fact of the matter is once you write down this Lagrangian, you very easily can appreciate the following trade-off. So if I plot my rate on one axis, and if I plot my distortion on the other axis, I cannot build neural networks that achieve both good distortion and good rate with some finite capacity. So any neural network with finite capacity is bound to stay on the right-hand side of this red line. Either you get good rate and very large rate and low distortion, in which case you're memorizing the data, or you get very large distortion and very small rate, in which case you're learning useless representations. You can kind of instantiate the rate distortion idea for our model, in which case we also have a classifier. So I'm going to add a third term to my Lagrangian. This is a classifier, which is simply the average classification loss computed over all the encoder outputs. You can also add other quantities to this, which is something that we are doing these days, such as the entropy of the model. This is a beautiful quantity to understand how many models in your hypothesis class can do well on this same data set. But let's not worry about that for now. Just like you have a rate distortion trade-off that is from information theory between R and D, in this case, you have a trade-off between R, D, and C. Instead of a line, you have a surface. And this surface is something very important and fundamental to all representation learning, right? So the model that we constructed is very generic. It is a model of all possible representations that I can learn by tweaking the different parts of the model. When you start training your neural network, you're really sitting somewhere outside this surface at very poor values of rate distortion classification. And your objective when you train pulls you down onto the surface. You cannot go below the surface because that is the best representation you can learn given your Lagrange multipliers lambda and gamma. And now you can understand the following game. So you can show that this surface is a convex surface in the functionals R, D, C, and S. And that is simply a formal way of saying that these functions are tied together to each other. You cannot change one without changing the other because you're working with the same parametric family, neural network, and a data set. in yet another formal way of saying this is that this surface is akin to what the first law of thermodynamics tells you for energy. So people might remember the first law. It says if I pump in heat, the heat either goes in as the internal energy of the system or as the entropy of the system. Well, this surface is exactly saying the same thing. If I pump in rate, you either get distortion or you get entropy or classification. Just like energy is conserved in physical processes, you have information being conserved in this model, and that's not really something that is magical, right? So we constructed the model in order to explicitly preserve this information. The beauty is that you can now measure what you're preserving and what you're not preserving. Now I can play the following game. I can design processes on this surface that travel anywhere on the surface. So we are simply like to instantiate a stochastic process. In this case, I would like to instantiate what I call an ISO classification process that travels along the surface and keeps the classification error constant. This is kind of motivated from a reversible expansion of an ideal gas where you don't change, don't add any work into the ideal gas, but you can change the volume, let's say. And this would be instantiated as follows. So the first condition is what we call the quasi-static condition. And that simply says that I would like my parameters to change in ways that keeps my model on this surface. I don't want you to fall out of the surface because this is a surface that I understand. This is a surface that lets me travel on all possible representations. I don't want to redo the work of training my model. The second one is the cool part. So this is a constraint that says I would like to preserve the classification error of my model. This is a training error, not the validation error, of course. But this is a stochastic process that can travel around on the surface while preserving the classification error in this case. Of course, you can plug in any other functional in place of C, and you would instantiate a stochastic process that preserves this functional. You can also execute these processes pretty easily for large neural networks. It's not that easy. And the reason is because these Lagrange multipliers lambda and gamma are just scalar parameters. So you can take derivatives of these pretty quickly. Running these processes is not any harder than, let's say, training a standard variation neural network. Here is one example. So this is the CIFAR10 dataset, and I'm plotting rate and distortion for constant values of classification. And you can see that I am on the rate distortion curve for different values of lambda and gamma. So I pick a particular lambda and gamma, let's say the blue one, I start my training, I fall somewhere on the blue curve, and then I keep changing them. I keep changing lambda and gamma as you see on the right-hand side, and can travel the surface at a constant classification loss. I can do
2 minutes, please.
Yes, thanks. I can do an even more interesting thing. So the surface that we talked about is really a surface that is defined by two things. It doesn't depend on the training. It is much more fundamental than that. It depends on the variational family that you're considering and the dataset, nothing else. I was changing the parameters of the family in the first experiment. Now I can simply change the dataset. So what I'm going to do now is take a source dataset, PS, and my target dataset, PT, and come up with some way of interpolating between these two distributions. This is simply a linear interpolation that I've shown here. You can think of a Wasserstein interpolation, and basically the math changes, but the algorithm more or less can also be instantiated. What I get is a time varying distribution, and I can again instantiate my same ISO classification stochastic process while my data distribution is changing. So think about what is happening here. I trained my neural network on a source dataset. I'm now changing my source dataset to go closer to the target dataset, and the model is tracking these changes in the dataset, and I can track these changes efficiently and effectively because I force the model to remain on the equilibrium surface. The equilibrium surface is a constraint that ties parameters of the model and doesn't let them fall out of equilibrium. This is a completely controlled mechanism for transferring representations, and that is what is unique about it. So today, when you do transfer learning, you train on the source dataset, try something on the target dataset, and if you don't like the results you get, there is nothing else you can do. But in this case, you can guarantee that the classification loss is constant along this entire process. It doesn't have to be constant. It can improve or decrease depending on what constraint you impose here. The key point is you can control exactly what you get. So long as your neural network is large enough, you will get a good result on the target data set. Here is one example. So the y-axis is the validation accuracy. When I'm transferring from a subset of CIFAR, there are about 4 vehicles in CIFAR, and there are 6 animals in CIFAR. So we're transferring from a source task with 4 vehicles to a target task with 6 animals. And if you do what we like to do today, you will get something like the blue line. Initially, I perform very poorly on animals. As I keep training it, I, let's say, get 80% accuracy in this particular case. If you directly train on animals, you get the green cross. You do well, but you don't do very spectacularly. If you do the ISO classification transfer process, you'll notice that the classification loss, although it is not constant in this case because we are using a small network to really push yourself or to remain on the equilibrium surface. If you take a large neural network, you always tend to be on the equilibrium surface. So we wanted to do something slightly different. So the classification loss kind of decreases, but it is still doing better than training from scratch, which is the blue line in this case. And the numbers are not really important for this small example, but the key point is you can control the performance of your transfer learning. And to summarize, we really looked at 2 flavors of transfer learning. The first one was how to transfer to data sets which have very few labels. In this case, your key objective is to pre-train a representation as regularized as you can make it, and then come up with good transductive ways of transferring. The second one kind of unlocks a little more into, it gives you a little different insight into this process. What are the general principles acting behind transfer learning? Please email all your questions to this email address. You can see these 2 papers. They're also in archive if you want to read more about this, and take questions if you have them now.
Thank you very much, Pratik, and for bringing the information theoretic point of view. There is a question, how does the transductive method scale with the size of this, as the loss term was ns plus nt?
Yes, that is a good question. So the transductive fine-tuning setup is fine-tuning the entire network on the source data set and the target data set at test time. Now you can choose to modulate how much of the source data set you use. That doesn't have to, that is more of a empirical question. Transductive methods scale in terms of, they also have a scaling factor in terms of how many test data you are using. They will take a little hit because you're actually explicitly changing your model on using the test data, but you also gain in terms of performance. So transductive inference will work much better than inductive inference that we are all used to, where we don't change the model with respect to text data. So you take a hit in the fine tuning, but yes, the performance more than makes up for it.
Thank you.